Welcome to some common polar curves. So we're just going to run through the equations for a few curves. You can find more in the textbook, but let's go ahead and start off with lines. So the easiest line to write an equation for is those that go through the origin. So note, if a line goes through the origin, then every single point on that line can correspond to angle omega. Some of the points in the direction of omega are for positive r. And then the points opposite omega are for r less than 0. So in this case, all points on the line have angle omega. And so our equation is simply theta equals omega. Now let's go ahead and look at a horizontal line. So we are looking at the line y equals a here. Let's pick some point on the line. We can draw our right triangle, which goes from the origin straight across the x-axis to the sort of the x value of the point, and then up to our point. So this would have angle theta, hypotenuse r, and then the opposite side would be a, right, the height of that line. So each point satisfies sine of theta is equal to a over r. If we rearrange this, this means that r can be written as a times cosecant of theta. If we have a vertical line, same idea. If we pick some point on this line, create our right triangle, which has hypotenuse, the radius going directly out to that point. And then the adjacent is a, opposite would be the y value. Okay. Then in this case, so I'm looking at the vertical line x equals a. Sorry, I didn't mention that. So in this case, we have that each point on the line satisfies that cosine of theta is equal to a over r. That therefore means that r should be equal to a times secant of theta. So if we do a cosecant theta, we get our horizontal line. A times secant theta gets us a vertical line. Then we have all other lines. So let's take the line y equals mx plus b. Right? Any point on the line, we can create a right triangle with the x and y coordinates. So I'm just going to call the x coordinate x. The y coordinate would therefore be mx plus b. We have radius r and angle theta. So for this point, each point on the line satisfies the fact that x is equal to r cosine theta. And we have also that sine of theta is equal to mx plus b over r. So if we plug in that r cosine theta for our x, and then multiply both sides by r, this becomes r sine theta is equal to r times m cosine theta plus b. If we rearrange this, we would have r times sine of theta minus m cosine theta is equal to b. And that therefore gives us that r is equal to b over. Let me give myself a little more room, one moment. If we just then divide through by that sine theta minus m cosine theta, we get that r is equal to b over sine of theta minus m cosine of theta. So given any line, we can write it in polar coordinates using this formula. From here, let's go ahead and move on into circles. So we're going to do 3 specific circles. Let's do the circle that's simply centered at the origin with radius A. Note each point on this circle has radius A. So each point satisfies or has radius A. And so we can simply take this equation to be r equals A. So a circle centered at the origin is r equals A. So the constant equations in polar coordinates are a circle centered at the origin or a line through the origin, as we saw earlier, depending on which of your variables is constant. Next up, we take a circle which is centered on the x-axis that just touches the origin, or that goes through the origin. So centered on the x-axis and through the origin. We're going to use a little fact. Here we have its radius is a over 2. So all the way across the circle is a, diameter a. Here we're going to use a little fact, which is if we pick any point on the circle and create a triangle that goes from that point to the ends of the diameter, in this case, where the circle intersects the x-axis, that triangle automatically is a right triangle. So in this particular case, this triangle that we're looking at has hypotenuse A and adjacent side R. So we wind up getting that cosine of theta is equal to R over A. And so our equation is therefore that R is equal to A cosine of theta. So you can imagine plotting these points yourself. When theta equals 0, we would just get R equals A. So that's when the angle is 0, we're on the x-axis at radius A. And then cosine gradually gets smaller as we head towards pi over 2. pi over 2, radius is 0, so that's where we're at the origin. And then cosine gets negative and more negative, so that would flip us, the radius therefore will be negative and will flip us across the origin into that fourth quadrant. If we look at a circle centered on the y-axis, again, that goes through the origin. Oops. All right, so again, through the origin. We can pull the same trick we pulled here. So this time around, our diameter that we use will be, so we're looking at a circle centered on the y-axis that goes, again, through the origin. We'll say it has diameter A. We're going to take the triangle that goes through our desired point. And that's endpoint. Other points are the endpoints of that y-axis diameter. Again, we get a right triangle. From the origin to the point is R. Our hypotenuse is A. And then the angle theta is actually not the angle right by the origin of our triangle with our triangle, but in fact the one up at top. So in this case, the R is our opposite. So we will use sine of theta is equal to R over A. And so this equation is that R is equal to A sine of theta. So here we have sort of what 4 of our trig functions look like. If R is equal to A sine of theta, we get this circle on the y-axis. R equals A cosine theta, we get the circle on the x-axis. We saw that R equals A cosecant theta was a horizontal line, and R equals A secant theta is a vertical line. So our trig functions get us some interesting shapes in polar coordinates. The very last thing we're going to look at, just for fun, is a rose curve. We're going to look at those that take the form R equals A sine of 2 theta over 5. So let's go ahead and switch over to Desmos here and see what these look like. So here is our R equals A sine of 2 theta over 5. Note, Desmos lets you just type in theta, T-H-E-T-A, and it will pop up theta, or you can click on the Desmos keyboard, and theta is where you find all the other letters of the alphabet. I then have set this for A equals 1. We get this lovely shape, hence why they call this a rose. If we go up to, and if we make A larger, so now A is 2, oops. There, A is 2. All it did is it made the shape a little larger. Right? So if R equals A sine of 2 theta over 5, we get this rather nice shape here that looks a bit like a rose. Right? So if I add this back into our notes, again, this is one very cool shape that we get with polar if we work with equations in polar coordinates. So this is for A equals 2. So R equals 2 sine of 2 theta over 5 gives us this very nice shape. So for your discussion this week, your job is to build your own polar curve that you think looks cool.